Next, let us come to the necessary and sufficient condition for the convergence of the improper integral a to b f of x dx. Okay, but here we consider the function f of x, this integrand f of x, to be positive. Okay. Okay, we test the convergence of the improper integral a to b f of x dx, where the integrand f of x is positive, and when x belonging to the open interval a, b, close to this interval, okay, is that there should exist a number k which is greater than 0, such that this integral a plus epsilon to b f of x dx should be less than this number k for every epsilon greater than, epsilon belonging to the interval this close 0, then open 0, then close b minus a. Remember, this is the necessary and sufficient condition for the convergence of the improper integral, but here we consider the integrand f of x to be positive. Next, we're coming to another way of how to check or how to find out whether the improper integral is convergence or it diverges to an infinite limit. We have another test, that is a comparison test of two integrals. Okay, let the function f and phi be two functions such that for all x belonging to the interval a to b, and the function or the integrand f of x is greater than or equal to 0, that is, this integrand should be positive. Similarly, this integrand phi of x should be positive, greater than or equal to 0. And also let the function f of x is less than or equal to the function phi of x. This function f of x is less than or equal to the function phi of x in this interval. Then, if the integral a to b phi of x dx converges, remember the big one, if it converges, then the integral a to b f of x dx is also, it converges. Okay, if the integral of this converges, then the integral of this is also convergent. And if the integral a to b f of x dx is not convergent, then the integral a to b phi of x dx does not converge. Okay, if this does not converge, then this phi of x does not converge. Remember, here I've shown you for the convergence when this a is the only point of infinite discontinuity. Next, we have another test which we call it as the practical comparison test. Here we have the ratio f of x by phi of x. If it converges to the limit L when x tends to a and L is neither 0 nor infinity, so it should be a finite value, but it should not equal to 0 nor it should not equal to infinity. Then the two integrals a to b f of x dx and the integral a to b phi of x dx either both converge or both of them do not converge. So they have a similar property for the convergence. So we're not going to the proof of those definitions or those tests for convergence. Now let us come to the first problem for in this problem the integral a to b dx by x minus a to the power n converges if and only if this n here should be less than 1. Okay, I'll explain you from the note itself. Let the function f of x equal to 1 by x minus a to the power n. So it is this function itself. Okay, here f of x we have a. If I substitute a here, if I find out f of a, then I will get an infinite value. Therefore, a is the only point of infinite discontinuity. For testing of convergence, I'm going to test in all different points for n. Okay, suppose this is for the value of n. Suppose here n is equal to 1. Okay, so here it will be n greater than 1, and from here n is less than 1. If you check your note, then I've written first I find out when n is not equal to 1, not at this value n equal to 1. I find out first for n greater than 1 and n less than 1. If you turn your page, you'll come to this stage. Okay, we'll come to this stage here. Therefore, for testing that improper integral, we have to find out the limit of when epsilon tends to 0 of this integral a plus epsilon to b f of x dx. Okay, you're going to have this limit of this here, but if n is less than 1, you're going to get this much. Okay, but if n is greater than 1, you're going to get this limit to be infinity. Okay, therefore it is convergent. That improper integral is convergent when n is less than 1, but it diverges when n is greater than 1. Next, we're going to test when the value of n is equal to 1. Okay, when n equal to 1, okay, if you find out this integration, you're going to get log of x minus a from a plus epsilon to b. Then if you substitute the limits, you're going to come to this stage, log b minus a by epsilon, and the log of this if you take epsilon tends to 0, okay, when you take epsilon tends to 0, then you'll get this limit to be equal to infinity. Therefore, this integral, it will only converge only when this n is less than 1. But if n is greater than 1, or if n is equal to 1, then this integration diverges. Therefore, a to b dx by x minus a to the power n converges if and only if n is less than 1. Okay. Using this problem, remember the sentence here. We're going to make use of this in other problems for finding out. Okay, you'll see in the next problem, using this and the comparison test, we're going to find out the convergence of some other example. If we examine the convergence of these three examples, then the first thing that we're going to make use is that comparison test, where you have to find out the limit of f of x by phi of x, and x tends to that point of infinite discontinuity. Okay, in this example, the point of infinite discontinuity is 0. If you put 0 in place of x, then you'll get an infinite value. Therefore, 0 is the only point of infinite discontinuity in this example. So we'll find out the limit x tends to 0. Okay, we're going to make use of this definition that test before and that previous example, where it is convergence when n is less than 1. Okay, we're going to make use of these two things. Okay, for the first example, here is your integrand f of x 1 by x to the power 1 by 3, then x into 1 plus x square. Okay, here 0 is the only point of infinite discontinuity. Now if you take phi of x to be 1 by x to the power 1 by 3, what will you have? Okay, you find out the limit f of x by phi of x, and x tends to that point of infinite discontinuity. Then you substitute the value of f of x and you substitute the value of phi of x. Then you get the limit to be equal to 1. Remember, the limit here is equal to 1, which is neither equal to 0 nor equal to the infinite value. It means that these two functions, f of x and phi of x, are having the same or similar behaviors. They are having identical behaviors, as I have written here. It means that if f of x converges, phi of x is also converging to a finite value, and if they diverge, then both of them should diverge. Okay, but here our function phi of x, this function phi of x, if you turn out your pages, you'll find out from the first problem that I have shown to you. Okay, I'll show you again. Okay, if you have a look at this example, this integral from a to b dx by x minus a to the power n, remember it converges if and only if n is less than 1. So here in our example also, this function phi of x 1 by 1 by x to the power 1 by 3, this function will converge to a finite value. In one word, we'll say it converges to a finite value. But since phi of x and f of x have identical behaviors, phi of x converges to a finite value, it also means that f of x also converges to a finite value. Therefore, we conclude that this integral from 0 to 1, okay, this one, okay, I'll show you. From 0 to 1, dx by x to the power 1 by 3, then 1 plus x squared is convergent. Next, let us try to explain. Let us come to an explanation for the second example, which is an integral from 0 to 1 dx by x squared, then into 1 plus x to the power 2, which is this one here. The integrand here is f of x equal to 1 by x squared into 1 plus x to the power 2. Here 0 is the only point of infinite discontinuity, since if you put the value of x equal to 0, or if you find f of 0, you will get the value to be infinity. Now we will proceed in the same way like as in the previous example, but here you're taking your phi of x equal to 1 by x squared. So let us find out the limit where x tends to the point of infinite discontinuity, f of x by phi of x. Okay, you find out, you substitute the value of f of x, then substitute the value of phi of x. You will get the limit to be equal to 1, which is neither equal to 0 nor equal to infinity. Therefore, since you get a finite value here, it means that these two integrals, this one and this one, which means f of x and phi of x, they have same behavior or identical behaviors. It means that if one of them is convergent, the other one is also convergent, or if one of them is divergent, then the other one is also divergent. But what you know is, for this integral 0 to 1 phi of x, I'll write here, it is this one, 0 to 1, the phi of x is 1 by x squared and then dx. Here 0 is the only point of infinite discontinuity. So comparing with that first example that I have done, here the value of n is equal to 2, which is the value of n is equal to 2, which is greater than 1. N equal to 2, which is greater than 1, it means that this integral is not convergent. It diverges to an infinite limit. Therefore, this integral will also is also divergent. Okay. Here we are only checking if the integral is convergent or it is divergent. If it is convergent also, we are not finding out that value. We only try to find out whether it is convergent or it is divergent. Next, let us have a look at this third example. 0 to 1 dx by x to the power 1 by 2, then 1 minus x to the power 1 by 3. In this third example, we're having 2 points of infinite discontinuity. The first point is x equal to 0. Since if you substitute the value of x in the integrand equal to 0, you will get an infinite value. Similarly, if you substitute the value of x equal to 1 in the integrand, you'll get the value to be infinite. Therefore, in this third example, I'll show you. If you have a look at your note, this is the third example. This one is the integrand. Okay. In your note, you have written 0 and 1 are the 2 points of infinite discontinuity of the integrand. Therefore, I'll show you in. Okay, I'll write here. Okay, you have 0, 0 to 1 f of x dx. But 0 and 1 are the 2 points of infinite discontinuity. So what you do is you take one point which is in between 0 and 1. Say, for example, we're taking that point to be 1 by 2. This 1 by 2 is in between 0 and 1. So you are trying to find out first from 0 to 1 by 2 f of x dx. Then you have to add with from 1 by 2 to 1 f of x dx. Now you have to find out the convergence of this first integral, and then you have to find out the convergence of this second integral. If both of them are convergent, then you have to conclude that this improper integral is convergent. Otherwise, if one of them or both of them are divergent, then this improper integral is divergent. But what you have here is, okay, you have taken this point 1 by 2, which is a point in between 0 and 1. Okay, the first one is 0 to 1 by 2 f of x dx, and the second one is from 1 by 2 to the point 1 f of x dx. Okay, and we have to check for the first one, we have to check the convergence at the point x equal to 0, and for the second one we have to check the convergence at the point x equal to 1, okay, respectively. Okay, let us do for the first one to check or to examine the convergence of 0 to 1 by 2 f of x dx. Okay, if you have a look here, this f of x, okay, you don't want to have this x to the power 1 by 2. Now, if you take phi of x to be equal to, if you take phi of x to be equal to 1 by x to the power 1 by 2, and if you find the limit of x tends to that point of infinite discontinuity, which is 0. Okay, f of x by phi of x. Then if you find out the limit, you'll get equal to 1. Here the limit equal to 1, which is neither equal to 0 nor equal to infinity. And for phi of x, okay, this is phi of x. What is your n? Your n is 1 by 2. 1 by 2, which is less than 1. Less than 1 means that this integration, okay, this integration 0 to 1, the integration, I have to take 0 to half first, phi of x dx, this is convergent. Okay, the first one is, this is convergent. It means that this first one is convergent. Now we'll have to find out the convergence of the second one. Now to examine the convergence of 1 by 2 to 1 f of x dx, we take another function and try to find out the convergence of that function. Okay, we take phi of x equal to 1 by 1 minus x to the power 1 by 3, and we find out the limit of x tends to that point of infinite discontinuity, which is 1. Since for the second one we have to find out the convergence at this point 1. Therefore x tends to 1, f of x by phi, so psi of x equal to, okay, you substitute the value of f of x and psi of x. Here I'm taking psi of x equal to this much. Okay, and you're going to get here, you are going to get that limit to be equal to 1, which is neither equal to 0 nor equal to infinity. Now the integration of half to 1 psi of x dx, okay, of this integrand, we have here n is equal to 1 by 3. 1 by 3, which is less than 1. Less than 1 means, if you go back to that first example, it means that the integral from half, okay, the integral half to 1, okay, I use psi, this is psi of x dx, this is convergent. Okay, that limit of the ratio is not equal to 0, nor, and is not equal to infinity. It means that these two integrals have identical behaviors. If this is convergent, this is also convergent. And what we have is, this integral is convergent. It means that this is convergent. So let me repeat. This is convergent. It means that this is convergent. This is convergent. It means that this convergent. So both of them are convergent. It means that this improper integral from 0 to 1 f of x dx is convergent.